So in this example, we're assuming we're standing on top of a building 15 meters up above ground level. And we drop a rock that's 5 kilograms. The rock falls, it hits this spring that's on the ground, a 3-meter long spring, and it compresses it. And we want to know, let's say, how much the spring compresses, or what's the final height of the rock. Where does the rock end up? So in that situation, if we look at this from the perspective of conservation of energy, what types of energy are changing from initial to final? We've got potential energy of gravity, potential energy of the spring, kinetic energy, and let's take those one at a time. Potential energy from initial to final for the rock, what type, or is the potential energy of the rock increasing or decreasing? Yeah, it's moving down. So we definitely have a decrease in potential energy because its height is decreasing. And we'll probably want to establish initial and final values of y. What about the spring? Is the spring gaining or losing potential energy from start to finish? Yeah, that's going to be increasing because what's our usual indicator for a spring potential energy? Yeah, the displacement, how far it's been stretched or compressed from equilibrium. It started off at equilibrium, it ends up not at equilibrium. So that means we do have an increase in absolute value of x. Absolute value of x because it shouldn't really matter whether it's stretched or compressed. Whichever direction you displace it, if you move it away from equilibrium, you're going to have an increase in potential energy. So we'll want to list out an initial x value and a final x value. We can actually start though by saying at the beginning, it's not stretched or compressed at all. There is no displacement. So what's x initial? Yeah, x initial is going to be 0. And x final, I think, is going to be unknown. We don't know how much it compresses. And what about kinetic energy? What do we know about the starting speed and ending speed? Starts at speed 0 because we're dropping it from rest, and ends at what speed? Yeah, it ends at also speed 0. So since it starts at speed 0, since we drop it from rest, and it ends at speed 0 because we're waiting for it to come to a complete stop, then overall there's no change in kinetic energy. There is certainly kinetic energy in between, but conservation of energy doesn't really care what happens in between, it just cares about initial and final values. So from initial to final, since the starting speed and ending speed are the same, there's overall no change in kinetic energy. So we can ignore that. We don't need to consider kinetic energy as part of the system. We just need to look at gravitational potential energy decreasing because it has moved down, spring potential energy increasing because the spring has been displaced. And that's it. And can we treat this as a closed system? Yeah, I think this makes sense as a closed system. It's relatively isolated. I think the only way it could really be gaining or losing a significant amount of energy in this case is maybe air resistance. But if we're talking about a rock, presumably a rock is fairly dense and compact. It's not really spread out in a way that's going to get a lot of air resistance. And it's also not moving terrifically fast. So I think we can ignore air resistance and treat this as a closed system. Which means these changes have to add up to 0. Any questions on that setup so far? So potential energy of gravity, we can use our usual mg delta y. Spring potential energy, we can use the usual 1/2 k times delta displacement squared. The squared, of course, being the reason why we don't care about sign, because we're going to be squaring it, and that always makes it positive anyway. So then if we start filling in, well, before we even fill in values, let's investigate those deltas. Because we want to be able to assign either values or names to all the unknowns. Like, do we know anything about the initial height? Yeah, that's 15 meters. I'm going to call that h for now, which is equal to 15 meters. But I think it might be more practical to write it as this constant just labeled h for now, and then we can fill in 15 meters at the end. But I usually find it useful to work in symbols as long as possible, and then fill in the numbers as the very last step. So we'll call y initial h, which we know happens to be 15 meters also. Do we know anything about y final? Yeah, we don't really know what y final is yet. We don't know, we know it's going to end up somewhere above ground level, but we don't know how far above. It doesn't quite reach ground level, but we don't know how much it compresses the spring. So I think what we're going to need to do then is establish a new variable. And I think x final might be the way to go here. We know it's going to be displaced a certain distance downwards. Let's say x final is some distance, let's just say some distance d. So let's establish a coordinate system here. So let's say capital D is the distance, the displacement from where the spring was to begin with to how much further down it's compressed. So that means x final is going to be D here. Or I guess since it's moved down, we should probably call that negative D, but it's not really going to matter because we're going to be squaring it anyway. But formally that would be negative D. It has been compressed, the length has been shortened by an amount d. So this delta x squared, that's going to be fleshed out to final squared minus initial squared, that's d squared minus 0 squared times 1/2 k. As for y, we're going to need to write y final. Ideally, we want to write everything in terms of just one unknown. So can we write the final height in terms of d? (15 minus d), except the thing is d isn't distance from the top down to where it ends up. D is just the distance from the top of the spring down to where it ends up. And what are we calling the height of the top of the spring? That's the equilibrium height, right? Which is how high up? Yeah, that's 3 meters, L. So that means if the top of the spring is L above the ground, and then we go down another D from that, what's this height above the ground? If this height is L, but we've gone down a D from there, yeah, that's 3 meters minus D. Or let's say L minus D. I'm going to call that L for now. We can fill in 3 meters at the end. But this means we now have a way of writing the final height in terms of those symbols. L minus D, or 3 meters minus D. So final height is going to be L minus D. Initial height is going to be H, which is 15 meters. So if we fill those in, final minus initial would be L minus D minus initial H. So now we have the whole thing written out in terms of a bunch of values we know: the mass, gravity, length of the natural length of the spring, the starting height of the rock, and the spring constant, and one unknown, this unknown value d. So we should be able to solve that for d. That'll tell us how much the rock gets compressed, or how much the spring gets compressed, and therefore how far below 3 meters the rock ends up. Any questions on that so far? So let's expand that out. Multiply this out, we get mgl minus mgd minus mgh plus k over 2 times d squared, and then the minus 0 squared doesn't do anything, so just k over 2 times d squared. Of these, what's the variable we're actually trying to find? Yeah, we want to know d. We want to know the distance that the spring gets displaced. So if we group these together, these terms based on d, we've got a d squared term, we've got a d term, and we've got a couple of terms that are constants, no d at all. So k over 2 times d squared, negative mg times d, and then two terms without d, which we can combine together. So just mgl minus mgh. Equals 0. A constant times d squared plus a constant times d plus a constant equals 0. What type of equation is this? Yeah, this is a quadratic. We've got a d squared in it. And since it's a quadratic equation, we should be able to use the quadratic formula in order to solve it. It might also happen to be factorable, but not as likely. But whether it's factorable or not, you can use the quadratic formula to solve it. So if we just use this a coefficient, this b coefficient, and this c coefficient in the usual quadratic formula, we should end up with a formula for the value of d. And you could also then plug in the numbers and figure out the actual numerical value of d. Any questions on that so far? So let's try that. At this point, I'm going to try actually plugging in the numbers because I'm concerned that these variables are going to just be a huge mess if we work it out in terms of the symbols. You certainly could. You'd end up with a general formula for how far it's displaced. But in this case, we're just looking for this one scenario, not a general case. And I think it might be better to just plug in the numbers at this point. So k is 100 divided by 2 would be 50 d squared. mg would be mass times gravity. We're assuming gravity is about 10 meters per second squared. So 5 times 10, negative 50. And then mgl minus mgh. M times g, we may as well factor that into mg times L minus h. Mg is still going to be 50. And what about L minus h? What would that be here? What were our values of L and h? The length of the spring and the height of the rock? Yeah, 3 minus 15 would be negative 12. 50 times negative 12 should be negative 600. So now we have a quadratic we can solve. Also, since everything here is a multiple of 50, it might be useful to divide by 50 first. Divide both sides by 50. We get 30, I think. And this one actually looks factorable. We could certainly use a quadratic formula, but I think this happens to be factorable Because what are a couple of numbers whose product is -30 and whose sum is -1? Yeah, -6 and 5. So our solutions then would be 6 or -5. And of those, which one should we be using? And why the -5 or why the 6? What were we assuming about the value of D in the first place? Were we assuming D was a positive number or a negative number? We weren't actually assuming D was a negative number though. We were assuming D was how far below L we get, which is why we were subtracting D from L. If you subtract a negative number, you end up with something larger. Like if D was -5, L minus D would be 3 meters minus -5, which would be 8 meters. We shouldn't expect the rock to end up above the spring. We should expect the rock to end up below 3 meters. So if we're subtracting D from L, we should be assuming D is a positive value. -12 instead of 30. Oh, that's right. I was thinking of 5 times 6 instead of 5 divided by 6. Okay. Yeah, thank you. That should be 12 there. For this one? Yeah. 600 divided by 50. Yeah, that should be 12. Thank you. So that changes the factorization. We're going to get D minus 4 times D plus 3. So D would be 4 or -3. But again, we should be expecting D to be a positive value. We were assuming D was positive because D is specifically how far beyond L we go. If D is negative, that means you don't actually reach the top of the spring. So we want a positive value for D because D is how much further past that point you go. So D would be 4. So that means you would that the rock would end up 4 meters below the top of the spring. What's the one problem with that though? Yeah, the spring is only 3 meters long, so it can't actually compress 4 meters. What do you think that means? If you actually set this up, if you set up this situation exactly as shown here and drop the rock onto the spring, what would you expect to really happen? If it should compress the spring by 4 meters, but the spring is only 3 meters long, what do you think is going to happen? Yeah, for one thing, it's probably going to break the spring because the spring is going to compress. What this tells us is that the rock will stop once it has compressed the spring 4 meters. The spring can't compress 4 meters though, so the rock is not going to stop because of the spring. The rock is going to hit the spring, compress it. At the 3 meter compression, that is when the spring is compressed down to nothing, the rock hasn't stopped yet, it's still moving. Of course, it can't keep moving because it hits the ground. But this means that the rock has not come to a complete stop by the time the spring is fully compressed. So the rock squashes the spring completely flat and then hits the ground and comes to a stop. But it's going to hit the ground hard rather than being completely cushioned and brought to a gentle stop by the spring. So what we might calculate instead, now that we know it's not actually going to come to a stop due to the spring, we could say, well, let's say instead it gets all the way to the ground. So H final is 0. Final length of the spring is compressed 3 meters. And then you could figure out how fast is it moving when it hits the ground. So in that case, we would incorporate kinetic energy. Or alternatively, we could say, what if the spring was longer? Let's say we extend this to 20 meters above the ground and also expand the spring by 5 meters. So if we started off 20 meters above the ground and had an 8-meter long spring, it'd be the exact same situation, just with more space to play with. And we still end up with the spring compressed by 4 meters. Any questions on that?
Can you please explain again why the D value is positive?
Because of the way we set up the coordinate system in the first place. We were declaring D to be how much further you go beyond the end of the spring. So as the rock is falling, it hits the end of the spring and goes some extra distance beyond that. We were calling that extra distance D. And we were treating D as positive. We didn't explicitly say so, but we were treating D as positive when we declared this final height to be L minus D. If D was a negative number, you would have to add a negative to L to make it shorter. So if we're calling this final height L minus D, we are implicitly assuming that D is a positive number. If it was a negative number, we wouldn't be subtracting it, we would be adding it.
Okay, that makes a lot more sense. Thank you.
Mm-hmm. And generally, the intuitive way we tend to think about numbers is assuming that those numbers is positive. Those numbers are positive. Like generally, when you think about adding something to a value, if you add something to a number, is that increasing it or decreasing it? Increasing, if the number you're adding is positive. If the number you're adding is negative, then you're actually decreasing the result. So that's kind of the reverse of the intuition. So keep in mind that the usual intuitive way that you tend to think about numbers is implicitly assuming that those numbers are positive. If you think of adding a number to something and increasing it, you're thinking of that number as being positive. If you think of subtracting a number for something and decreasing it, you are thinking of that number as positive. So keep that in mind. It's generally a good idea whenever you're declaring a new variable in some sort of coordinate system, decide for yourself as soon as you declare that variable, whether you want to treat that variable as a positive value or a negative value. If you're treating it as a negative value, then subtracting it will increase the result and adding it will decrease the result. So intuitively, it's often easier to just define values as assume this is a positive number and work from there. Any other questions on that so far? All right, then let's take a look at this as a graph also. For purposes of the graph, I'm going to say assume that the spring was longer to begin with. Let's just stretch out this whole system. Let's add some extra space underneath. Let's assume that the spring was originally, let's just extend this by another 5 meters. Let's assume that the spring was originally 8 meters long. It ends up at 8 meters minus 4 meters. So the final length would be 4. The initial height of the ball then would have been 20 meters. And the final height of the ball would be 4 meters. So let's assume the ball starts off 20 meters above the ground. It falls, it hits an 8 meter long spring and compresses that 8 meter long spring to 4 meters. The math should still work out the same way. We just now have enough space for the spring to compress the way it's supposed to. So with that situation, let's see if we can draw out a graph of the energies involved. And we'll probably want a graph of presumably height, the y value, versus the energies. And what are the most important heights here? What Y values do we really care about most? Yeah, 20 meters and 4 meters. And also there's something important happening at what other height in between those? Yeah, at 8 meters, the ball hits the spring. So from 20 meters down to 8 meters, we only care about gravity. From 8 to 4, we care about both gravity and the spring. So I'm going to put marks at 4, 8, and 20. So 4 meters, 8 meters, and 20 meters, some very important stuff is happening. And let's see if we can graph some of these energies. We're going to want to graph the potential energy of gravity and the spring potential energy, of course, but also in between, we do care about the kinetic energy. So let's start with the kinetic energy. I think a couple of them are going to be easy. Like at the very beginning, at 20 meters high, what's the kinetic energy? Yeah, we know we start with no kinetic energy at 20 meters. We also know that when we reach 4 meters, the ball has come to a stop. So that's also 0 kinetic energy. It's the in-between stuff that we don't know how to graph yet. So let's graph the potential energies instead. Gravitational potential energy, what's our usual formula for that? Yeah, mgy. And we know mg, 5 times 10 is 50. So this is really just 50 times y. And what would that look like as a graph if you just graph E equals 50 times y? Yeah, this is a linear function. It's just going to be a straight line through the origin. And we could even plug in some data points. Like for instance, if it just has a line with slope 50, we know it's going to go through 0, 0. At the highest, it's going to be 50 times 20. That's going to be 1,000. So 1,000, I think, is going to be the highest energy we have on this graph. We put in some in-between points there. So we'll just mark off the energies in hundreds of joules. We know we start off with potential energy of 1,000 joules when we're at 20 meters off the ground. And 0 joules when we're at ground level. And we could even fill in some in-between values. For instance, 4 times 50 would be 200. 8 times 50 would be 400. And overall, we just get a straight line. So the entire potential energy of gravity graph is just a straight line. And in theory, that just keeps going on forever in both directions. In practice, we only need to consider between 4 meters and 20 meters, but the graph itself of 50y should keep going. So that's our graph of potential energy of gravity. What other potential energy do we want to draw here? We definitely want to draw E total, but yeah, first we should draw potential energy of the spring. So if we use our usual 1/2 K times displacement squared, but we're going to have to be careful about displacement. We've got 1/2 times spring constant We're using 100 for that, 1/2 times 100. But for displacement, this isn't a graph of x, this is a graph of y, the height. So how could we write out displacement in terms of y? Like if you're at a certain height, how would we write out the displacement based on that height? Like for instance, let's say you compress the spring 1 meter. What's your new height? Yeah, you compress the spring by 1 meter, you're now at a height of 7 meters. Because the spring is 8 meters long. When you hit the top of the spring, you're at a height of 8 meters. If you compress 1 meter beyond that, your new height is 7 meters. Or what if you hit the top of the spring and compress it by 5 meters? Compress the spring 5 meters and your height is 3 meters, right? Compress 5 meters, you're still 3 meters above ground level. What if you compress the spring by x meters? How are you calculating the 7 meters, the 3 meters? How do you figure out your height if you're compressed a certain amount? Yeah, we just subtract x from 8. You fall until you're at 8 meters, and then you compress the spring x meters beyond that. Your new height is 8 minus x. And note, we're still assuming here that x is positive, which is why we're subtracting it from 8 rather than adding it to 8. So our displacement here, if height is y equals 8 minus x, if you solve that for x, add x to both sides, subtract y from both sides, x is 8 minus y. The lower your height is, the more displaced the spring is. So this should really be 8 minus y squared. That puts this in terms of y instead of in terms of x, which means we can actually graph it on this y versus energy graph. What this is going to be, this is still going to be a parabola, but it's now a parabola, it's now a quadratic written in vertex form instead of in standard ax squared plus bx plus c form. This 8 minus y squared tells us that the vertex is going to happen when y is 8. Because if y is 8, 8 minus 8 is 0. So the spring potential energy is 0 at 8. Go to the left, that is in the negative y direction, we'd get more potential energy. In the positive y direction, we'd also get more potential energy, but we're not actually going to include the right half of the parabola. Because if the rock hasn't fallen to 8 meters yet, it hasn't hit the spring yet. Before the rock hits the spring, how much potential energy does the spring have? Yeah, before the rock hits the spring, like when the rock is up here, the spring has no potential energy. If the rock has fallen some of the way but hasn't hit the spring yet, the spring still has no potential energy. So the spring potential energy is 0 for all of this time. Until the rock actually hits it. Then it starts gaining potential energy. So it's really just potential energy of the spring equals 50 times 8 minus y squared if y is less than or equal to 8. For y values greater than 8, the potential energy of the spring is just 0. But as soon as it hits the spring, the potential energy starts to grow. And it should grow quadratically. It's going to be a parabola shape. In fact, if we plug in 4, we've got 8 minus 4 would be 4 squared. Is that going to work? Did I do the calculation right? We know we're actually going to hit 0 here. Because if we're talking about 0 kinetic energy, oh, but we also have 200 joules of potential energy, right? So we could figure out how much spring potential energy there is. In fact, we could do this just in terms of E total. If we go back to the very beginning, We've got no kinetic energy, no spring potential energy, 1,000 joules of gravitational potential energy. So what's E total? Yeah, E total is 1,000. And since E total is constant, that's just going to be a horizontal line. Which means by the time we get to 4 meters, when the ball comes to a stop, at 4 meters, we've got no kinetic energy, 200 joules of gravitational potential energy. So what should we expect the spring potential energy to be? Yeah, it should be 800. Because we've got 200 already used up as potential energy of gravity, no kinetic energy. So we need an extra 800 so that these 0 plus 200 plus 800 adds up to 1,000. And now we know what this parabola is going for. We know we're going to have a parabola from 0 to 800 here. So it's going to be shaped something like this. So there's our spring potential energy graph. 0 until the rock hits it, and then growing quadratically as the rock compresses it. Any questions on those graphs so far? And again, mathematically, this parabola could keep going, but we may as well stop it here because we know the rock doesn't go beyond that point. Likewise, this right side of the parabola exists mathematically, but we don't really need it because the rock doesn't actually interact with the spring during that time. Likewise, we may as well sort of fade out this portion of the potential energy of gravity graph. Although that portion exists mathematically, we don't really need to consider it physically because beyond the 4 meter mark, there's no further motion of the rock. And I think at this point, now that we've got the total energy value and both potential energy graphs, all the energies involved except kinetic energy, we can now draw in the kinetic energy values. And one way we could do that is to just start plotting a few points. For instance, let's say we look at, let's say at 8 meters. At 8 meters, we've got no spring potential energy. We've got 400 joules of potential energy of gravity. So what would the kinetic energy have to be to make those still add up to 1,000? Zero plus 400 plus what? Yeah, 600. So at this location, at the instant the object hits the spring, it's got to have 600 joules of kinetic energy. Likewise, at 12, we've got 600 joules of potential energy, so 400 joules of kinetic energy is going to make those add up to 1,000. At 16, we've got 800 joules of potential, so we've got to have 200 joules of kinetic. Overall, what sort of shape should we expect these to form? Yeah, if potential energy is decreasing linearly, then kinetic energy is going to be increasing linearly, because those are the only things that are changing. As soon as we get past 8, though, things change. Because as we go, if we're at 8 and we keep moving in the negative y direction, potential energy of gravity is still increasing, but potential energy of the spring starts increasing. So that means that things get more complicated. We're going to need to consider both. What you could do is at each location, you could say, add up this value of potential energy of the spring plus this value of potential energy of gravity. Add those up, see what's left over from 1,000, and that's how much kinetic energy is left. But we also know kinetic energy has to reach 0 by the time it gets to y equals 4. And what shape should we expect it to be in between? Yeah, it's going to be a curve. And specifically, it will be a portion of a parabola. Because we have kinetic energy equals E total minus potential energy of gravity minus potential energy of the spring. This is a constant. This is a linear function. this is a quadratic function. If you add a quadratic plus a linear term plus a constant term, the result is still a quadratic. You get something t or something y squared plus something y plus something. That's still a quadratic. So this portion of the graph is still going to be a parabola. It's just a parabola that has to curve to hit 0 here. So I would expect the kinetic energy graph to look something like this. Linear until you get to 8 meters, and then curves to become a parabola. So with this graph, you could now predict the kinetic energy at any location. So at any single y value, like let's say y equals 15, you could just use the graph to predict the kinetic energy and the potential energy at that location. So this is a much more complete picture of what's going on in between, whereas the conservation of energy final and initial approach only looks at those initial and final values. Could potential energy of gravity ever be a quadratic? Not if you're specifically graphing y versus energy, because potential energy of gravity is just a constant times y. So if you're graphing y versus energy, potential energy of gravity will always be a linear function. If you're graphing something else versus potential energy, like let's say you've got some curvy mountain path or something. If you were graphing, let's say, distance traveled along the path versus energy, then potential energy of gravity is going to be a shape that depends on the curvature of that path. So for instance, if you have like a skateboard ramp that's shaped like a parabola, and you're graphing x versus potential energy instead of y versus potential energy, then you would get a quadratic because the shape of the ramp is a quadratic. But if you're graphing y versus potential energy, then potential energy of gravity will always be a straight line. Any other questions on that? All right, then I will see you next time.